Hi, and welcome to Fundamentals of Power webinar. I'm your presenter, Bill Driver. I'm a product manager at Yokogawa, and you can find my information here if you'd like to contact me with any questions following the webinar. I want to thank you for investing your time today and learning more about power measurements. We have a lot to cover today on the topic of fundamentals of power. So at the end of the webinar, I want you to be familiar with the basics of power measurements, how to make physical measurements, how to choose the right measurement equipment, and how it applies to some real-world examples. Before we jump in, I want to give some background on Yokogawa. Yokogawa has over a 100-year history in power, as they were the first to make and sell electric meters in Japan. They've expanded to 84 companies worldwide and are in 59 countries. The United States operation pictured here is based in Noonan, Georgia. This is where we host our services, support, and calibration teams. And we have our A2LA ISO 17025 accredited Cal Lab here as well. So leveraging off the deep power knowledge that comes from a company like Yokogawa, we have continued to provide training webinars to help you do your job and understand these concepts better. We recently hosted sessions on tips for more accurate measurements and measurement isolations and motor drives. You can find those on demand. The topics in this session are fundamental to power measurements, and we plan to host additional topics in the future to go deeper on some. And go deeper on some as well. So leave me feedback at the end of the session for other topics that you'd like to see. The fun and challenge of a webinar with fundamentals in the title is whittling it down to an hour or less. Such complex topics here can be probably covered within 2+ hours. Also, there are college courses dedicated to some of these topics, and the challenge is going to be, how do I hit enough to give you the background to follow through? So I'm just going to maybe glance over some topics and maybe not go deep on others, but just know this should give you a good fundamental understanding of power and power measurements as we described in the agenda. Many of you are likely professionals in manufacturing or test, and you're here for different reasons. So some of you may need to understand a product's performance in detail, including designing and or testing efficiency. So there's probably those of you that work with standards, we could probably cover those within a 2-hour webinar alone, but many in our industry have standards that we have to adhere to. And it goes without saying when we talk about power measurements that safety is paramount. We'll make sure that we cover how to do these measurements safely. And today we're going to focus not just on the power, but the measurements of power with the purpose of understanding efficiency, safety, and cost. So power spans many industries, but it's the small nuances of power measurements in these industries that really make us specialists in our field, which you can see the measurement parameters listed on the right. For the purposes of brevity, we're going to narrow this down to motors and home appliances. Home and office appliances like a computer monitor or LED TV are not always in use. We not only want to measure the power when they're on, but we want to measure their power when they're off to make sure they're not consuming too much power and not costing us money. On a motor that powers our vehicle, we want them to be the most efficient they can be. So if it's electric, we want the best range. Or if it's a combustion, we want the best fuel economy. If a test report requires a power measurement, it may want you to measure real or active power, apparent power, reactive power, or instantaneous power, or RMS power, AC power, DC power, or harmonics power. Today we want to talk about all of these different types of powers. What's the difference? And to help you better understand when this is asked of you in your test requirements. Here's a closer look at the actual measurements that a manufacturer is concerned with, so it can benefit the consumer. As you can see, it isn't as simple as capturing a voltage and current with a digital multimeter and then multiplying together. It's much more complex. When testing a monitor, there are some terms like standby power and active power. On the motor side, we're going to see terms like phase, AC and DC, harmonics, power factor, and efficiency. When we make these power measurements on a monitor, which instruments do I use? What are the trade-offs? How do I connect the power line to my instrument to make the measurement? And some questions, why do I want to measure apparent power versus real power? And if it asks me for harmonics, why do I want to measure them? And how many do I need to measure? What is power factor? So we hope to answer these questions But before we do, we need to start with some basic definitions. Let's discuss what some of these terms mean. What is power? Power is the rate at which a device consumes energy, defined as work over time, and we measure power in watts. Watts. We're familiar with watts when choosing a light bulb. A higher watt rating, the brighter the bulb. That's because a 100-watt bulb consumes more power than a 60-watt bulb. There's also more heat output of a 100-watt bulb. We call this the calorific effect, since much of the energy is lost as heat. Watts are defined as joules per second. When measuring power, it's important to understand how much energy is consumed by a device, as well as being able to measure efficiency. It is often about energy consumption, but in some circuits, there's energy generation that we need to be aware of and measure. More on that later. When we talk about efficiency, we're talking about energy losses or waste. We don't want waste. If I'm providing power to a device, I want that power to all be used. If it's not, then we lose efficiency. Efficiency is the ratio of power out to power in. When we talk about efficiency, efficiency is the ratio of power out to power in. We'll talk more about efficiency in the examples below. As you can find more and more ways to generate power, we need to find more and more ways to use it. So conserving power and developing more efficient devices is important for the world. For example, a large percentage of the world's power is used to power industry. This can be quantified to roughly 42%. Now, did you know 2/3 of that is used to power motors? So think about what a small percent increase in efficiency can do to our energy savings. Be pretty profound. We can't calculate efficiency or power without starting with voltage and current measurement. To review voltage and current, it's important to understand their relationship with each other by reviewing Ohm's law. These laws apply to DC circuits. When we calculate power in an AC circuit, things get a little more complex. So in this chart, I is current, E is voltage, R is resistance, and P is power. For some references to power in this webinar may appear as U or V. They are the same. Also, current may appear as A or I. They're also the same. But since this session is about power, P equals I squared R, or P equals E times I, voltage times current. Those are going to be the most common equations that we're going to use for power. I mentioned Ohm's law applies to DC. So DC stands for direct current, meaning there's a direct and constant source of current and voltage that flows in one direction from the source. So sources of DC are typically power supplies, batteries, and solar cells. The easy thing about DC is there's a fixed magnitude associated with the voltages and current in a definite direction, which is indicated by a plus or minus. Power in a DC system is volts times current, measured in watts. AC stands for alternating current. This is defined as a waveform that varies in time in both magnitude and direction. The DC waveforms were flat with a constant magnitude, but AC waveforms are sinusoidal waveforms. So that makes power measurement more complicated. Well, let me clarify. Not all AC waveforms are sinusoidal, but we'll get to that. The period, defined here as T, is important in AC waveforms because the nature of the sinusoidal waveforms have a period when it repeats. This can be used to determine the frequency of the waveform. Since the sinusoidal waveforms are periodic, we need to incorporate another variable into the power equation, power factor. The power equation is similar to DC, but we need to add power factor. So in this illustration, there is no power factor or phase shift. Due to the nature of AC circuits, there are three types of power that make up what we call the power triangle. There's no longer a simple term to use in an AC circuit like we can for DC. To make sure we use them correctly, true power, active power, and real power are all used interchangeably. I'll try to use true power throughout the presentation to be consistent. For true power, power equals volts RMS times current RMS times power factor. RMS is root mean square, and we'll talk about that in a minute. These equations will make more sense when we define the elements of the power triangle in a minute. Yokogawa uses this equation to calculate true power and true RMS measurements of any waveform, which includes all harmonic content. It's the instantaneous voltage times the instantaneous current integrated over time, T. We can easily calculate the RMS voltage and current by taking the root of the integrated square. The advantage of this method is it's true for all waveform types and shapes, since we often deal with distorted waveforms. The previous equations work for sinusoids. Let's take a quick tangent from power and define RMS. RMS stands for root mean squared. RMS of an AC waveform gives the same heating effect as an equivalent DC power or power dissipation in a circuit. AC waveforms fluctuate between positive and negative voltages and cycles. DC voltage is just constant one-way voltage that doesn't have cycles. Because of this difference, it's very difficult to compare the two. This is where RMS value is important. It gives us a standard to compare the amount of power that an AC waveform and DC waveform can give to a circuit. RMS voltage is the DC equivalent of an AC waveform, so we can compare the dissipation with both the AC and DC power waveforms. If we have an RMS waveform on an AC circuit and it's the same as the DC waveform, then we know they both give off or dissipate the same amount of power in a circuit. It's important to note that RMS only refers to AC signals with varying magnitude. RMS is not used when we talk about DC. There are other types of voltage measurements made, including peak, peak-to-peak, RMS, and average. This is confusing when you see a voltage measurement with no indication because you don't know what to assume it means. It often refers to peak. A common mistake made when comparing values is assuming RMS voltage is equal to the average voltage. They're not equal, but there's a way to convert from one to the other. You're often faced with a term that you want to convert, let's say peak to peak to RMS or average. Fear not, we have a conversion table. You can use the scale factors to apply from one to the other. One of the most common used conversion is peak voltage to RMS. Voltage peak equals voltage RMS times square root of 2, or said differently, RMS equals peak voltage divided by the square root of 2. Using this chart, you can use the scale factors to go from any value to any other value. Going back to the types of power in an AC system, we have an angle called phi. Phi is related to power factor. Power factor, often indicated by the symbol phi, equals the cosine of phi for sine waveforms, also called the displacement power factor. Phi is related to power factor. Power factor, often indicated by the symbol lambda, equals the cosine of phi for sine waves, also called the displacement power factor. In complex waveforms, power factor equals active power divided by apparent power. This is called the true power factor. Power factor defines the phase angle between the current and voltage waveforms, where I and V are the magnitude of RMS values of the voltage and current. And it's generally expressed as either a decimal value, for example 0.95, or as a percentage, 95%. It's also unitless. A purely resistive circuit is where the voltage and current waveforms are in phase, meaning the real power consumed is the same as the apparent power. This will provide a power factor of 1, which is cosine of the angle 0. This is called a unity power factor. The power triangle has 4 parts, P, Q, S, and phi. In our AC power calculation, we define true power, reactive power, and apparent power. It's easiest to show these and their relationship with each other in the power triangle. True power, measured in watts, is the power that does the work. This is the power that is consumed by the resistive part of the circuit. Real power in an AC circuit is the same as power in a DC circuit. Reactive power, sometimes called wattless power, is measured in volt-amps, reactive, or VAR. It does no work and is stored in exchange by inductance and capacitance, but it has a big effect on the phase shift between voltage and current. There's no reactive power in DC circuits. The reactive power supplies the reactance in the circuit. Apparent power represents the vector sum of P and Q, given in volt-amps. This represents the total power consumed by a circuit, even though the real power that does the work can be a lot less. Phi is the phase angle in degrees. The larger the phase angle, the greater the reactive power. Let's look at a nice cold mug of beer to help us understand this example. Using a mug of beer will help. Active power is the power doing the work, or the beer that is quenching our thirst. The reactive power is taking up room in the mug, but not quenching our thirst, just as it would take up room in a conductor. Apparent power is the size or volume in the mug. Simple, right? Okay, how does this relate to electricity again? Let's look at 2 mugs of beer. When we pour a beer, we want as much beer in the mug as possible, and the least amount of foam. So this analogy works well to explain power factor. The mug represents the volume that can make up the apparent power. When you pay for a beer, you would expect it to be filled to the top. If you paid for a beer and received the beer on the left, you'd be upset. The beer that's doing the work is the active power. That's the beer quenching your thirst. The reactive power is not doing anything other than giving you a mustache when you're drinking. You would much rather have a beer closer to the right, which is closer to a unity power factor. Putting this into electrical terms, if you had an electrical system with a power factor similar to the one on the left, the conductors would need to be sized to carry the voltage and current calculated by the apparent power, but you're only using the active portion of it. So you must account for the reactive wasted power. With a larger conductor comes more cost, weight, and losses. Let's apply this to a real-world example. Here's our 3-phase motor from earlier. Since the power triangle is a right triangle, we can use the Pythagorean theorem to solve for unknown values. If we use a motor plate, for example, we can use this data to compute the apparent power given the true power and the power factor. On this specific motor, P equals 1.5 kilowatts, or 1500. Power factor is given in a range of 0.85 to 0.79. We'll use 0.85 for our calculation. Using our equation for power factor equals P over S. And we can solve for S, which equals 1765 volt amps. If we want to solve for phi, or reactive power, we could do that as well. If I was installing this motor, I could use this data to verify that I'm using the correct winding type, gauge, right motor drive, which will provide power to that 3-phase PWM motor for the given load. We've been talking about power factor, but not explaining what causes it to change in a circuit. Power factor shows how phi, or power factor, can affect the power calculations. In a purely resistive circuit, there's no phase difference between voltage and current, so the power factor is unity. The angle is 0, and the cosine of 0 is 1. But the addition of capacitors and inductors changes the phase relationship. There's a mnemonic taught in many schools to remember the AC current and voltage phase angle relationship in inductors and capacitors. It's called Eli the Iceman. In this mnemonic, E is voltage, L is inductance, I is current, and C is capacitance. In an inductive circuit, indicated by L, voltage comes first, so it leads current. In a capacitive circuit with the C, current comes first, so it leads voltage. When current and voltage are plotted on the same axis, it's clear to see the phase change and the different. Again, when current and voltage are plotted on the same axis, it's clear to see the phase change with the different load types. The angle phi indicates the difference in phase between the 2 waveforms, as we previously discussed in the power triangle. Sinusoidal waveforms of the same frequency can have a phase difference between them. And this represents the angular difference that we usually use terms of lead, lag, as well as in phase and out of phase. They're commonly used to indicate the relationship of one waveform to the other. But when presented mathematically in this way, it is difficult to visualize the angular phasor difference between the two. One way to overcome this is to represent the sinusoids graphically within a spatial or phasor domain form using vector diagrams. This is achieved by a rotating vector method. Basically, a rotating vector, simply called a phasor, or we'll interchangeably use the word vector, is a scaled line whose length represents the AC quantity. It has both magnitude, which is the peak amplitude, and direction, phase, and it's frozen in time at some point. So the vector has an arrowhead at one end. It signifies the part that's the maximum value, VRI, and partly the end of the vector that rotates. Generally, vectors are assumed to pivot at one end around a fixed 0 point known as the point of origin, while the arrowed end, representing the quantity, freely rotates in an anti-clockwise direction, represented by omega. The anti-clockwise rotation of the vector is considered to be a positive rotation. This is a single-phase vector diagram of both an inductive load and a capacitive load. In the image on the left, the current vector lags behind the voltage vector as the two waveforms are the same frequency. The image on the right shows a current vector leading the voltage vector. Either way, One vector is designated as the reference, and the other will either be leading or lagging with respect to this reference. Unfortunately, I don't have a beer example to demonstrate, but an example of an inductive load is an induction motor. An example of a capacitive load is a fluorescent light with a ballast. Why are we so concerned about the leading or lagging of voltage and current waveforms? Well, we go back to why we're measuring power in the first place. We want efficiency. We want to conserve power. We want to design a circuit with minimal power factor to deliver the most real power to our load. Converting back to the XY time domain view, power calculated in a resistive load has no phase angle, so power equals U times I, voltage times current. In a non-resistive load, inductive or capacitive, with a phase angle, power is calculated as U times I times cosine of phi. In the system, power is both positive and negative. Positive power is consumed and negative power is generated back into the load. So quiz time. Is the non-resistive load shown here capacitive or inductive? Those of you talking to yourself that answered inductive load are correct. We see the voltage waveform labeled E starting at 0, with the current waveform labeled I crossing 0 at a time later. So voltage is leading the current, and according to Eli the Iceman, that is an inductive load. In the prior example, if the inductive motor is 3 phases, a phasor diagram will look like this in a Y wiring configuration. So each voltage phasor is 120 degrees separated from the other. The respective currents lag the voltage, making this a 3-phase inductive system. In a purely resistive system, there would be no single phase angle. A system with voltages 120 degrees apart is said to be balanced. Here's an example from a Yokogawa power analyzer showing the 3 phases of voltage and 3 phases of current. You can see the lambda for the first measurement is 9.85. Second one is 9.74. The other is 9.96. As we've seen throughout the webinar, when dealing with alternating currents and voltages, it's assumed that they're pure sinusoidal in shape with one frequency value called the fundamental frequency being present. But that's not always the case. There's other types of waveforms that are commonly referred to as non-sinusoidal or complex waveforms. These complex waveforms are generated by common electrical devices such as switching transformers in a motor drive or electric ballast in a fluorescent light. The resultant waveform may not even resemble the original sine wave. Of the many types of complex waveforms, a very common one is the square wave. The square wave shown here is constructed from multiple sine waves at different odd frequencies, or multiples of the fundamental called harmonics. The harmonics we speak of are high-frequency waveforms superimposed onto the fundamental frequency, and that distorts its wave shape. By applying a Fourier transform, we can break down a complex waveform into its basic components, for which to be sine waves at different frequencies, amplitudes, and phases. The fundamental waveform can be called the first harmonic waveform. The second harmonic has a frequency twice that of the fundamental. The third harmonic has a frequency 3 times the fundamental, and so forth. In this example, the square wave has only odd harmonics for a reason we're not going to get into in this webinar. Harmonics have been around over the past decade since the introduction of electric drives for motors, introduction of fans and pumps, power supply switching circuits such as the rectifiers shown here. This is part of a motor controller or an AC drive. An AC motor drive is AC inputs that cuts and chops the waveform. It goes to a capacitive bank and it filters out for DC, and then it goes to an DC to AC inverter stage. So here are a lot of fundamentals being introduced due to the chopping and cutting of these waveforms. Just how much distortion is caused by harmonics? So in our two examples, the rectifier circuit, like the one in our AC drive, we can have a contribution of 20% harmonic current in the fifth harmonic. And using the fluorescent light example, we can have 29% current within the third harmonic. Because harmonics can cause excess heat, wasted power, and potential damage to our equipment, we want to be able to accurately measure them so we can both understand what's present and help us reduce them. The reduction of harmonics is another topic outside of this webinar. To measure harmonics, luckily we have products like power analyzers and oscilloscopes to make. This example is from the Yokogawa WT5000 power analyzer. There are many pre-programmed functions to calculate and show harmonic detail. On the left is a harmonic table. This specific power analyzer can measure up to 500 orders of harmonic content. On the right, we can isolate the specific harmonic order to see the voltage, power, current, and power factor attributed to that specific harmonic. We've covered a good amount of fundamental pieces of power. Let's look at these systems in our examples again, but let's look at their wiring diagrams and how they differ from one another, from one phase to three phases. These details can help us determine how many inputs for voltage and current we need to make a proper power measurement. Each of these devices has a unique wiring scheme, and understanding these will help us in making our power measurements. A computer monitor uses a single-phase two-wire system, which is very common and used when loads are mostly lighting or heating. Standard frequencies of single-phase are either 50 to 60 hertz. The system consists of a positive and negative wire that are rated to carry the rated voltage and current. The ground wire is sometimes used for safety. We often abbreviate wiring systems. This one specifically we call 1P2W, meaning one-phase two-wire. The V in the circle indicates a voltmeter, and the I indicates a current meter. The washer and dryer in our homes uses a system called a single-phase three-wire system, or 1P3W. The system is also called a split-phase system. Its primary advantage, it saves conductor material over a single-ended single-phase system, while it requires a single phase on the supply side of the transformer. You can go in your laundry room today and you'll see a plug that resembles this, but don't stick your multimeter in there. It should be safe. Each voltage line carries the potential, so the line-to-line measurement in this example would be 240 volts, and 120 volts would be the measurement from line to neutral. A three-phase circuit is commonly used to power large motors and other heavy loads. This specific configuration is a three-phase delta configuration, 3V3A. Three-phase circuits are more economical than an equivalent two-wire single-phase circuit at the same line-to-ground voltage because it uses less conductor material to transmit a given amount of electrical power. In this wiring diagram, there's no neutral, so voltage measurements are made between lines or phases, so the resulting voltage measurement is called line-to-line. A variant on a wiring technique when three voltages and three wires are present is the three-phase delta, but using 2 watt meters, 3P3W method. This method reduces a voltage and current meter and can calculate the third based on Blondell's theorem. This is less expensive because it requires one less wattmeter. Blondell's theorem states that the total power is measured of one less wattmeter than the number of wires. Since we have 3 wires in this system, 3W, we can measure the power with 2 meters. There's a derivation of this, but we're not going to cover it in the webinar. In the three-phase Y system, 3P4W, voltage measurements are made from line to a common neutral as shown below. This method is used when a neutral is present, but often there's not a neutral present, so preferred wiring methods are often dictated by the wiring available from the source. In this system, the 3 phases are balanced, meaning theoretically there's no current flowing through the neutral since the 3 currents summed together will equal 0. Often a neutral is present in a motor winding, but not available for a measurement. When there's no neutral present, we can measure voltage in a delta connection, or line-to-line. The voltage between 2 phases or lines for delta connection, let's use V, where V is the voltage across the phase windings. For a star connection, the voltage between the 2 phases would be square root of 3 times V. What if you need to measure individual phase voltages line to neutral, that you don't have access to a neutral? The Yokogawa power analyzers have a delta star transformation function that uses data from a delta connection that you can use to compute to a Y connection, or line to line versus line to neutral. This solution does not require any additional hardware, false neutral, or floating of voltmeters. Here's what the waveforms look like in a delta connection, measured line to line. On the top are the line to line voltages, below are the phase currents. Voltages may look confusing because they're not 120 degrees apart as expected in a 3-phase system. They're 60 degrees apart because they're connected line to line. The phase angle between the currents is 120 degrees. The vector diagram of a delta connection will clearly show the 60-degree phase angle between the voltage waveforms, as shown here. This is 60 degrees. Where in the Y, between the red currents, that's 120 degrees. When we decide on a measurement system to make our measurements, we need to make a few considerations to determine the best instrument. Given efficiency is becoming more and more significant in our measurements, we need to make sure the instrument and all of the measurements have better accuracy than what we're trying to measure. Putting these all together and adding all the sources of error are important before we start probing onto our devices or wiring anything. We've determined we need to calculate voltage and current to make any power measurements. So for voltage measurements, these are taken in parallel. There are a few methods for making these measurements, each with trade-offs. The first is the wattmeter. This wattmeter is taken from our WT5000. It has voltage inputs on the top and current inputs at the bottom. Second is a high voltage differential probe. This actually has a differential amplifier in an architecture and subtracts the positive and negative leads. This advantage is it's rated for definitely high voltage and lower loading capacitance. The third is a passive probe. Passive probes are really common throughout labs. They have a high voltage rating, and they're relatively inexpensive with a high bandwidth, but the trade-offs are going to be accuracy. There are a few more options for current measurements. The top two use a shunt resistor to make current measurements. Remember the Ohm's law, voltage equals current times resistance. So with a known resistance, the shunt, current equals volts divided by resistance. Knowing that, we can calculate current. The wattmeter is what we use in power analyzers. There is an integrated shunt in the wattmeter that's actually compensated for temperature. There's other methods with various trade-offs, and each method has a purpose, but there's really not one right answer. You just have to understand the trade-offs to make the best decision. Clamps and coils are not recommended to use with power analyzers because of their accuracy, but we do have connections for them for your convenience. Let's look at the clamp and flux gate in more detail. The biggest difference between the clamp-on probe is you can open the core and place it around a conductor. On the closed-loop flux gate, you have to remove the conductor and place it through. The clamp-on probe uses a Hall effect sensor, and the closed-loop flux gate uses a flux gate sensor. To help quantify the trade-offs, accuracy is going to be the biggest consideration. The clamp-on is roughly 3% accurate, and the closed loop is about 0.05% accurate. The closed loop is more difficult to install, as we mentioned, but it's preferred for more permanent or semi-permanent test setups. The clamp-on probe is ideal for flexibility and quick answers, often used with oscilloscopes. So now we know the trade-offs for making voltage and current measurements. Now we need to decide what instruments are we hooking these up to. We categorize these instruments into averaging and waveform analysis. It's an important distinction between these instruments because they calculate power differently. In general terms, the trade-off of these instruments are the same with the current measurements, really accuracy versus flexibility. On the accuracy side, you have the averaging style. On the flexibility side, you have the waveform analysis. Main differences between these instruments is bandwidth. Generally, power measurements are properly digitized with 1 to 2 megahertz. But if some other signals on your test end are of higher voltage or higher bandwidth, a power analyzer might not be adequate. You generally want to choose an instrument that has 3 times the frequency of the fundamental. A power analyzer is going to have a higher resolution ADC as well. This is the nature of ADCs on the market since there really aren't any 18-bit ADCs 500 megahertz and up. The last is accuracy. The scope is rated to generally 1.5%, where the power analyzer can go down to 0.01%. The main differences between these two instruments is the level of detail provided in their specifications. Power analyzers specify accuracy on voltage, current, and power from DC to the full bandwidth of the instruments. Our DAC and oscilloscopes will generally spec usually a DC, and sometimes that's going to be typical and not guaranteed. Quick little plug. Yokogawa takes accuracy very seriously and wants to be transparent in the specifications. Interpreting specifications can be a daunting task given how many variables are part of the equation, such as the voltage reading and the range, and the current reading and the range, and the wiring, and the frequency and the power factor. We have a free uncertainty calculator available on the web that will tell you the range of accuracy given for the analyzer or wattmeter being used. You enter all the instrument settings and you will know exactly the accuracy range within that setting. The same argument of accuracy applies to harmonics. If you're using an instrument to provide harmonic details, the accuracy of the instrument also applies to those measurements. On the scope side, you'll have a basic FFT without a spec, and you'll be subject to spectral leakage. On the power analyzer side, you have a spec again for voltage, power, and current, and using a tracking PLL, you'll have a lot less spectral leakage. Most DAC or oscilloscope products don't list specifications for harmonics at all. Power analyzers give the same level of detail up to the full frequency, as you can see here. So is this good or bad? Well, Depends on what you want. If you want a general idea of harmonics present in your system, accuracy specs aren't required. An FFT will suffice. If you're designing a product to comply with standards like IEEE 519, or are threatened by the power company to shut down because you're placing too much dirty power back onto the grid, you may be willing to change instruments and get a little higher level of confidence in your device with a power analyzer. To summarize, an averaging style analyzer is ideal for benchmarking and it's to give you the most accurate power measurements. A waveform analysis solution is ideal for viewing waveforms and looking at various types of signals at the trade-off of accuracy. There's no right or wrong answer. It really all depends on your application. Now we can put a bow on everything that we've learned. Let's start with our computer monitor as an example. If we manufacture a computer monitor and wanted to have Energy Star spec, which is SPEC, or IEC 62301 certification, we would need to test for the standard. One specific test is standby power. Standby power is the energy consumed by the device when not performing its main function. So standby power is energy divided by time, and this is an average active power measurement. This is the preferred method as it works on both steady and fluctuating power sources, and it's the most accurate method. For this test, I hooked up Dell monitor that is Energy Star compliant to my Yokogawa WT1800 power analyzer. I connected the voltage lines in parallel and the current lines in series. My laptop was connected and I was running the compliant software. Using the power consumption measuring software from Yokogawa, I ran a standby power test with my monitor in a powered off state. This is an example of the test report, the IEC 62301 test report, and the data dump here stamped in time in a CSV format. So the software is available on all models of my Yokogawa power analyzers. For our three-phase motor example, we're going to make connections to our AC drive. So we need 3 voltage and 3 current connections at the input to the drive. For DC input power, we need 1 voltage and 1 current. For AC output, we need 3 current and 3 voltage. So for harmonics, we can measure test points 1, 2, and 3 to see what harmonics are being put back on the AC mains. Test points 5, 6, and 7 will tell us what harmonics were created by the AC drive. For mechanical power and efficiency, we'll need to monitor the motor input at test point M. This will require a 7-element power analyzer, 3 for AC in, 3 AC out, 1 for DC. We'll also need a motor input for the mechanical measurement from the torque sensor to make our efficiency measurements. Let's look at the various efficiency measurement test points. In this 3-phase motor example, we have 4 different efficiency measurements we can make. For AC to DC, we want to see how well our circuit converts to DC using our rectifier circuit. For AC drive efficiency, we want to compare the measurement and let's do this again. In this 3-phase motor example, we have 4 different efficiency measurements we can make. For AC to DC efficiency, we want to see how well our circuit converts to DC using our rectifier circuit. For AC drive efficiency, we want to compare the measure In this 3-phase motor example, we have 4 different efficiency measurements we can make. For AC to DC efficiency, we want to see how well our circuit converts to DC using our rectifier circuit. For AC drive efficiency, we want to see how well we can measure the losses to the rectifier stage, DC stage, and IGBT stage. Motor efficiency will measure those losses attributed only to the motor, and last, we can measure the losses through the entire system. For efficiency measurements, we need to configure the motor input from the torque sensor. In the efficiency measure setup, we need to define the equation we want to use. This is power out divided by power in. The input power to the motor is the output of the AC drive. In our setup, we used elements 5, 6, and 7, which were represented by sigma B. Here's a screenshot from a WT5000 Yokogawa power analyzer showing the input to the motor connections on the output of a drive. It is a low horsepower motor. It's not very loaded, so the voltages and currents are pretty low. The top waveforms are the 3 waveforms shown in PWM in a 3V3A wire configuration shown here. The bottom waveforms show 3 phases of current. They're rather noisy and they're shown without any filtering. We show RMS voltage and current measurements P, S, and Q, lambda, theta, and we have our fundamental shown here. Here's a vector diagram of the same three-phase motor. This is a great example of where this would come in handy for visual, showing if there's any imbalances or phase shift. Another even more useful feature for this view, especially our customers who primarily use 3V3A, is it gives an indication if the unit is miswired. If you're already a power analyzer user and not getting the numbers you want, here's a few things to consider. First, check the manual from the vendor to make sure that you're using the right wiring configuration. Also, you might have the reverse polarity. You can quickly verify this using a vector diagram. If your accuracy doesn't seem right, you might not be using the lowest range. As you saw in the accuracy measurements, it depends on the range, and so a higher range setting is going to give you more error. If you're using a probe, those are not going to be the most accurate ways to bring in voltage and current. You might want to use a more direct source. You also want to check your sink source. Sometimes if you're using current for your sink, if you're using voltage for your sink, it could be noisy, so we recommend using current. Also, there's settings for your frequency filter settings and your line settings that can clean up both your measurements as well as your synchronization. If there's not enough bandwidth, you'll need to know your fundamental frequency, and if there's not enough, you might need a new instrument. But if you have too much bandwidth, you might want to use a filter. Your efficiency measurement could be correct within that screen I showed before. Make sure that you have the right numerator and denominator. And you might not be using a lowest current element with your CT, meaning if you're using a current transformer, it outputs 1 amp or 2 amps. So you'd want a current element that matches, not up to 50 amps, because you'd be giving up accuracy. In summary, we've covered a lot in a little time. I hope you understand the difference between AC and DC power, the power triangle, how power factor influences power, as well as harmonics, and I hope you know how to properly order a draft beer. You should be able to confidently choose the right equipment, make the right power measurements, and interpret the measurement results in setup menus. Yokogawa has a full suite of power analyzers, power scopes, oscilloscopes, and data acquisition products, including voltage and current probes. We have the expertise in making power measurements and have a network of field sales and application engineers to help with whatever measurement challenge you may face. Please consider making Yokogawa your trusted partner in power. If you happen to be in the market for an analyzer or oscilloscope, please know that there is a trade-in promotion where we can take any of your units you have around the lab and apply a discount to a new working unit. Again, thank you for your time. You can find more information at tmi.yokogawa.com. And you can contact us at webinars@us.yokogawa.com and support@us.yokogawa.com. Thank you.